Hello students, I hope you are in the right place. We are looking at the first H3 lectures, that is molecular stereochemistry. In case you are wondering what about your friends in other JC, are they learning this as their first topic? Our understanding is that most of the JC will cover molecular stereochemistry first, okay? Because that will give you a very good foundation in visualizing structure that is essential for many of the topics that follows. Okay, and if you want some advice, I think I can safely say that molecular chemistry at the beginning may seems a bit easy, okay, but it is actually more difficult than it seems. So it is important for you to have a good foundation of this topic, because later on we will not have a lot of time to do a lot of revision on it, because it is kind of understood that you know some of the basic ideas on doing certain things lah. Like for example, the simplest example I can quote you would be the drawing of the chair conformation. Okay, if you look at the learning outcomes, it seems to be very short. Okay, just five parts, okay, or 5 subparts. That is true for a lot of the H3 learning outcomes. They seems very short, but the question appear otherwise. So I think do not be fooled by the very short and concise learning outcomes. In case you are wondering where to get the information, okay, you can actually go to Google, okay, and then you type SEAB syllabus 9813. 9813 is the syllabus for the H3 chemistry. Okay, do not type 9812 because that is the old pharmaceutical chem syllabus. Okay, so you click this, it will lead you to a PDF file. Okay, you can actually download the PDF file if you wish to. So you just download it, and then please keep it in your phone, right? Because it is very useful. You can always refer to the learning objective as and when you need to refer to them. Okay, of course it's written as 2022 over here. If you wish to, you can download the latest one, that is 2023. There isn't much difference. Okay, so I think Mr. Lee last year has already gone through some of it with you, or maybe asked you to look through it, so I will not go into very big details on what is the difference. Yeah, so if there's a need to, I can create another video on it. If not, it is absolutely not necessary. Okay, so you notice that there are a few broad topics in H3. Number one is spectroscopic methods. So we're going to do quite a bit of it towards April. Okay, April-May period. And then later on you have further organic chemistry topics on mechanism. So molecular stereochemistry is part of it. I also don't know why they put it under here, but probably because if you have a good understanding of stereochemistry, then it will help you to appreciate mechanism better. Okay, especially one of the mechanism that you require to do quite a bit of it is actually elimination. Okay, and then we will move on to physical organic chem. Okay, so that will be one of the topics you're going to learn this term, and then the usual mechanism which you'll be familiar from H2, that is nucleophilic substitution, elimination. Okay, and that's about it. So the syllabus seems very short, so don't be deceived by it, because the questions that come out can be quite varied. Okay, and then after that you get some of these things which you also get to see in your H2 syllabus document. Okay, so from page 14 onwards, they are quite similar to what you have in H2. Okay, so I will not go through it. But of course, I often tell my H2 as well as H3 students is that please look at the glossary of the terms, because the glossary of the terms kind of tells you the common words that will appear in most, if not all, the H2 and H3 questions you're going to have. So these command words are very important, because understanding them will allow you to come up with answers of appropriate length or appropriate depth. Okay, so go through them on your own. Okay, if there's a need to, we'll also have a video on that, but that's the next part. And then of course you have a data booklet at the end, which is extremely useful for H3 students. Which part of the data booklet is useful besides the usual H2 stuff? I would say this particular page, from page let me just scroll over. Okay, so that is 34 on nuclear magnetic resonance data. So these are the chemical shifts of the protons, so you can go through them if you wish to, and then of course the infrared spectroscopic data. Yeah, that's about it. So these 2 pages are quite important for H3. Okay, so if you've gone through the syllabus, you might notice that I will often tell the students that you should not refer to them in exams. If you need to refer to them, that will be more of to confirm your suspicion or to confirm what you are thinking about a certain chemical shift or a certain a stretch wave numbers. Okay, to fully appreciate it, of course, you have to go through the course. Okay, so that's a syllabus document. Please download it, keep it in your phone, keep it in your laptop or your iPad or whatsoever, and anywhere you go, if you need to, please refer to them. Okay. Other than that, I will jump straight into the lecture. Okay, so we'll look at the various portion of the contents. Okay, so there will be 3 broad topics which we will discuss: conformational analysis, that is topic 2 on isomerism, and then of course we have cis-trans. Cis-trans, you have learned them in introductory organic chem. There isn't much difference from what you have learned in H2. Remember that H3 is a built up from H2, so you shouldn't be thinking that you're going to learn new things. You are not learning new things in the sense that you are not relearning what you learned in H2, but what is happening here is that we are going a little bit more in depth into the nitty-gritties. Okay, in our case here will be the naming. So in this case, the easy convention. Okay, later on you will learn that it's called the CIP rules. And then of course, topic 4, we are dealing with enantiomerism and diastereomerism. Diastereomerism is something that is new. Okay, this is new for most, if not all of you. Okay, and then of course we have annex at the end, where we are trying to explain between conformation and configuration, and then the importance of stereochem in nature. We believe that your introductory organic chem notes will have talked about this briefly. Okay, from why is stereochemistry important. Okay, and of course Annex C, we're going to talk about Fischer projection. Maybe not in the lecture setting, but something you can read about. Okay, it's not in syllabus. It used to be in the old pharmaceutical chem syllabus, but they have decided to reduce the learning load of the students. They have taken it out from the H3 curriculum, but nonetheless it's not very difficult. If you're interested, you can read about it. Okay, there's this nice cartoon which we have sourced online. Okay, it's about Snoopy learning stereochem. It's actually quite interesting. If you wish to, you can just go through it on your own. Okay, if you can catch the joke, that is. Okay, and then of course, first of all, we're going to go into introduction. Again, we look at a broad view. Okay, what exactly is isomerism? Okay, so it can be summarized using this particular diagram. Okay, so basically, the broad view, the broad understanding of isomers are that they have the same molecular formula, okay, but they differ in the arrangement of the atoms. Okay, the difference could be in terms of connectivity, okay, in terms of connectivity, or in terms of their position in space or their projection in space. Okay, so broadly speaking, for isomerism, there are 2 broad categories. We have constitutional isomerism and we have stereoisomerism. Okay, so what exactly is constitutional isomerism? You have learned them in H2. We believe that. Okay, if you forgot about it, please go and review. Okay, so for constitutional isomerism, in H2 or maybe in secondary school, you learn it as structural isomerism. So basically, same molecular formula. Okay, but the atoms, they are bonded to one another in a slightly different way. Okay, so in terms of connectivity, it's different. Alright, so that is constitutional isomerism. Okay, we will not discuss in details. If you need the details, please look at your introductory organic chemistry lectures. Okay, we will focus a lot more on stereoisomerism for H3. Okay, for stereoisomerism, again, there are 2 broad categories. We have conformational isomerism and configurational isomerism. Okay, so for configurational isomerism, we are actually dealing with how the atoms project themselves differently in space. Okay, a very straightforward way of explaining this would be looking at cis-trans isomerism. So for example, if you have trans built 2 in versus cis built 2 in terms of connectivity, the carbons are all bonded to one another in a straight chain. Okay, they are in one line fashion. So from carbon 1 to carbon 2 to carbon 3 to carbon 4, from one end to the other end. But the difference is that they are being projected differently in space. For trans, they are opposite each other. Okay, the methyl group are opposite each other, or you can look at it from the perspective of the hydrogens, they are opposite each other. But for cis, they are on the same side. Again, sometimes students get confused. What do we mean by same side or opposite each other? You have to visualize a division of space in between them. So for example, this red line is a space, so we say that the methyl group are opposite each other. Yeah, in this case, they are on the same side over here and here. And for the trans, they are opposite each other. Okay, so that is what we meant by projection, or being projected differently in space for the groups. Okay, for enantiomerism, we are looking at how the central carbon atom, or it need not be a carbon, but usually for H2, for simplicity, we look at a carbon atom, right? Okay, when it is bonded to 4 different groups, okay, its mirror image and itself are non-superimposable. Okay, you notice that. Okay, again, when I have a carbon bonded to 4 different groups, so for example, I have a carbon here, I have a H here, for example, and then let's say I have a Cl, and then I have a group projecting out, let's say it's a Br, and then another group projecting in, let's say it's a F. If I have a mirror plane here, I have a F here, the carbon, the Br, the Cl, and the H. Okay, if I try to rotate this molecule, okay, along the CH axis in this direction and try to fit it in, you'll notice that, I'm just going to draw it above, you'll notice that the H and the C will be in the same axis because I'm rotating about the CH axis. I will be able to put the Cl in the same position here. So in this case, this particular portion will be the same. Okay, but what's going to change is that the Br and the F will be projecting differently from one another. Okay, in this case, what is projecting out towards you will be F, what is projecting away from you will be Br. So in this case, we say that the F and the Br here, they project themselves differently in space. But again, we are looking at it from the perspective that we are keeping HC and Cl in one plane. You can always say that we do not keep them in the same plane. We change the plane to, let's say, H, C, and F. Can we do that? We can do that. Then you will notice that Cl and Br project themselves differently in space. Yeah, so this is the way to understand enantiomerism. Basically, it is not possible for you to try to fit your mirror image onto itself. Okay, does it mean that a chiral center is absolutely necessary? No, a chiral center is not absolutely necessary. I can give you an example. For example, if I put my eyes here, right, and then I have something that spiral downwards in a clockwise fashion, okay, like this, okay, clockwise fashion like this, right? So it goes like that when you look from the top. Okay, if I try to draw the mirror image, you realize that it will actually spiral the other way around. Okay, so this is an example of a helix lah. So from clockwise to anti-clockwise. So it is impossible for you to superimpose one onto the other. Do you notice that? Impossible for you to superimpose one onto the other. Unless, of course, you change the... of course, you can simply say that, oh, I just elongate the rope and then I change the way it rotates or change the way you twist it. Well, I mean, you can do that, but you should also be aware that in nature, right, they are in a certain helical fashion due to the fact that there is some form of stabilization, either in the form of hydrogen bonding or some other type of interaction. So it is not as if you want to do it, you can do that easily, okay? Because in thermodynamics sense, nature will want to tend towards the most stable state, right? So it will have a preferred way of arrangement. So it's not something that you can disrupt that easily. Yeah, so in short, enantiomerism need not or rather in quite a number of cases, you can have enantiomerism without a chiral center. Yeah, that is something you got to be aware of. Yeah, and that is probably the greatest groundbreaking ideas that you will learn in H3, because H2 tends to limit the students' frame of reference or ideas about enantiomerism to a carbon having 4 different groups, but that is often not the case. Right, so we can go on and on, but I think I have to stop here. Yeah, because the emphasis on the next portion will be on conformational isomerism, which I think we probably needs quite a bit of time to discuss. Okay, so I'm just going to move on to this portion on conformational isomerism. You'll notice that earlier on I did not actually touch on it. I deliberately jump into configurational isomerism, that is on enantiomerism and cis trans. Well, the reason why I do that is obviously because all of you at this point in time, you are familiar with these two forms of isomerism, because you have learned them under introductory organic chem. For conformational isomerism, unless you read out on your own, or you did some chemistry Olympic kind of training, if not, you will not be very familiar with it. Okay, we'll use ethane as the example. Yep, so I will not use the lecture notes for now. I will first go to chem draw. So I'm going to draw ethane molecule out, and then after that I'm going to just use chem 3D. Okay, so this is ethane molecule. Chem 3D is good for teaching because I can zoom in and out. You can see that. Okay, you probably do not need me to color code, or rather to label the atoms for you. Black is carbon, white is hydrogen. Okay, so I think that should be quite obvious to you, I hope. Okay, so I'm just going to rotate it. Okay, so this is ethane. You notice that this ethane molecule is static. Okay, and obviously all the molecules we draw in our work, they are all static. But of course the truth is molecules are free to rotate about their single bonds. Okay, that's why we normally say that in most of the time the rotational barrier about a single bond is almost barrierless. So the heat from the surrounding is sufficient to overcome the rotational barrier. Okay, so that means that it can do a free rotation. You just rotate depending on the temperature of the surrounding. Okay, so what we normally do is we can do an optimization to minimize the energy of this system. Okay, so it doesn't really matter whether you understand what it means. Okay, so this is ethane. Yep, so when we look at ethane in this particular fashion, okay, we say that this represents one conformer. Okay, yeah, so as we rotate about the CC double bond, you will realize that the angle made between these two carbon, this carbon and this hydrogen, okay, and the carbon behind and the hydrogen behind. So that means we're looking at this particular angle being made, right? Okay. As you rotate one round from 0 to 360 degrees, you'll notice that there is infinite number of forms it can exist in. So these infinite number of forms, right, we call them conformers. Okay, so or you can call them conformational isomers. Yeah, it's a bit confusing, I understand sometimes. Okay, so and that is why when you go on to university and you learn about conformational analysis, right, certain university or certain professors do not believe in calling conformers isomers. So you notice that there is like a slightly different school of thoughts. They will think that, oh, conformers are actually not isomers. So again, H3, we are not here to argue whether you agree or don't agree. Okay, it's basically it's a different school of thoughts, I feel. So there isn't a need to argue whether it is an isomer or it's not. Okay, but when you take a snapshot of the molecule, okay, imagine you have a camera, okay, and you have a camera that is fast enough to capture molecular motion. So if you take a snapshot of it, like what we have here, this is one conformer. Okay, so are we able to analyze it over in Chem 3D? Actually, we can do that. So I'm just going to show you. So I'm just going to look at the dihedral angle. Okay, you notice that the dihedral angle is 60 degrees. Okay. Why is it 60 degrees? Because this is a position where it is the most stabilized. Okay, later on you're going to learn a special name to this conformer. Okay, we call it staggered conformation. Later on we'll recognize that. Okay, so I'm just going to go to Chem 3D, right? I'm going to look at dihedral. So I'm going to do a single angle plot. Okay, so you get this plots out. Okay, I'm just going to explain to you. Okay, it might be a little bit confusing for you now, but rest assured that everything is okay, under control. Okay, I'm just going to shift this up a little bit. Okay, I'm just going to make it smaller. I'm going to remove the yellow labels. Okay, because I think it's a bit irritating. Okay, so I'm just going to remove the yellow labels. I hope I can do that. All right. Okay, I can do that. Okay. I'm just going to show you different views lah. Okay, so if you prefer to look at it like that, it's the normal kind of ways you are used to looking at the skeletal structure. Remember, the skeletal structure, you tend to do a zigzag, right? Zigzag like this, right? Or I can show you from this particular view. Yeah, so later on you will learn that when we look at it from this particular view, right, we are actually drawing what we call a Newman projection. Okay, yep. So I'm just going to just rotate it so that it's easier. Okay, so I'm just going to point my arrow towards this end. Okay, that will be the maximum. Okay, I'm just going to click. Okay, what do you notice? The dihedral angle, right, is 0 degrees. So can you see that? Are you able to understand why this is the most energetically unfavorable conformation? Yeah. One of the ways you can explain is because the hydrogen, they are facing each other. So that means that they will experience unfavorable repulsion between the hydrogen electron cloud. However small it is, there is still some form of repulsion. Yeah. This particular conformation, later on, there will be a name ascribed to it. It's called eclipsed conformation. Okay, so later on, going to learn two extreme conformation, eclipse and staggered. So this is the eclipse one. Earlier on, we saw the staggered conformation. That's the minimum. Okay, so this is the most stable one. Why is it the most stable? Because none of the hydrogen are facing each other and they are at the maximum distance from the hydrogen behind them or in front of them, depending on the perspective. Okay, you notice that if I click here, okay, and I move it along, can you see that the back is rotating? Can you see that? Okay, so I'm going to move it along until I get the top again, and then this is where I get the eclipse conformation again, and I'm going to shift it down, and then the back is rotating until I get back the staggered conformation. Yeah. Okay, so that is why earlier on we said that there are infinite number of conformation, because technically speaking we can go to 1 decimal place or even 2 decimal place or 3 decimal place, okay, for the angle, the dihedral angle. Okay, so technically we can have infinite number of conformation for a particular molecule, okay, or any molecules. But when we use the simplest example to focus on, we are looking at ethane. Okay, and there are 2 important conformation we're looking at. Okay, so if I'm going to summarize, the most important conformation are staggered, okay, over here, where the hydrogens are at maximum distance from the one behind them, okay, and eclipse. Okay, so I hope this particular illustration gives you a decent understanding. Like, I wouldn't say I wouldn't say that you will get a very good understanding of what exactly is going on, but I hope it gives you a decent understanding, so that it will form the basis of several discussion we have later on. Okay, so I'm just going to remove this. Okay, going to go back to the lecture notes. Okay, yeah, so the lecture notes is trying to explain to you a lot of things which I tried to explain to you earlier on using Chem 3D. Okay, so if you read through them, I think it will make more sense now. Okay, so I wouldn't attempt to go through the details, as you know my style. I mean, I think there is no point in going through the details by repeating all the words. Yeah, you can read through them on your own. Yeah, but do take note that the simplest way for you to understand this is really to build models, and you can build models by actually getting toothpicks and styrofoam balls, or even some of the models that we're going to use in our classrooms. Okay, but what is important is we want to show you different representation, and the most important representation we thought we want to show you is what we call the Newman projection. Okay, so this Newman projection is very important because I think it helps you to visualize things a little bit better. Okay, so I think you know what we meant when we show you the Newman projection. Okay, and but probably you might need a little bit of explanation. So let's say we have a displayed formula that looks like this. I know this is very ugly. This displayed formula is quite ugly. Yeah, but over here, right, this particular carbon is this carbon that is right in front of us, and then we just draw a circle. Okay, so the circle here represents that we are not able to see the carbon behind us. Okay, and of course this particular CH3 group is over here behind us. Okay, I'm just going to circle them in red, and of course you can't see this carbon. Okay, so these are the one in red. Yeah, so learn how to draw Newman projection because it's very important, extremely important in fact, and quite a number of times the students have difficulty, your seniors have difficulty translating from a normal displayed formula to a Newman projection. Okay, so do take note of this. Right, okay, so now over here we're going to have a displayed eclipse conformation of ethane. Now the eclipse conformation is a little bit tricky. Yeah, why do we say tricky? Because technically speaking, right, the H behind us, you can't draw it out because it's blocking by the H in front of you, correct? Yeah, but normally we will not attempt to not draw them out, but we'll just draw them out in this particular weird manner. Okay, so maybe I can sort of teach you how to draw it. So the first thing you need to do is just draw the CH3 in front of you like this. Okay, just draw it like this. Okay, and then after that you try to give it a little bit of an angle, but just a little bit of an angle, so maybe like this, just to show that it's actually behind you. Okay, so like this. Okay, and then of course form the good habit of indicating the bond angle, which is 0 degrees. Yeah, something like this. Yeah, so this is called eclipsed, and then the other one, this is called staggered. Make sure you are very familiar. Okay, you get yourself familiar in drawing these two conformations. Okay, again, the staggered one is the most stable, the eclipse one is the least stable. Okay, so Newman projection, I have gone through what exactly it is with you. Okay, so eclipse conformation, normally what we are talking about is that there is, why is it unstable? Okay, it's because of electronic repulsion, okay, between the hydrogens. Yeah, okay, then there is also another school of thoughts people talk about, that is what we call torsional strain. This term is a big term, so make sure you learn how to use it, but if you don't know how to use it, then don't use it. Okay, the torsional strain is basically the electronic repulsion between the electron pairs of the CH bonds. So you can see that the CH sigma bonds are facing each other, so there exists unfavorable repulsion. Some of you might be a bit confused. Why would there be repulsion? Like you might be thinking about, wouldn't electron density wants to overlap continuously? You might get confused with concepts such as resonance. But normally, right, you need to be aware that 2 electrons, or rather 4 electron interaction tends to be unfavorable. Okay, what do we mean by 4 electron interaction? Okay, a CH bond has an electron pair, the CH bond has another electron pair. So 2 plus 2 is 4. So normally 4 electron interaction tends to be repulsive in nature. You're going to learn more about them in university, of course, but and of course when you learn more about molecular orbital theory, but we won't go into details on them. Okay, and then of course the potential energy diagram, which was what I've shown you earlier on in Chem 3D, right, is something you need to learn how to draw it. Okay, of course you are not supposed to memorize the values. I mean again, H3, very little things to remember, but what you need is more of the skills. Yeah, okay, so in general, right, CH repulsion is about 1 kilocalorie per mole. So 1 kilocalorie is about 4.2 or 4.18 kilojoules per mole. So if you multiply that by 3, that's about 12 kilojoules per mole. So yeah, that is being reflected by the difference in staggered and eclipse conformation in this particular potential energy diagram. Okay, and remember that these values are not absolute, if you know what I'm trying to say. So which means we are not saying that for for staggered conformation, it has a potential energy of 0 calories per mole. No, we are not saying that. Remember this. We are not saying that it has a potential energy of 0 calories per mole. It's always relative. So relative to the eclipse conformation, it is 12 kilojoules per mole more stabilized. Or you can discuss it the other way around. For eclipse conformation relative to the staggered conformation, it is 12 kilojoules per mole more unstable, or destabilized by 12 kilojoules per mole, something along those lines. Okay, so when you sketch out the potential energy diagram, right, make sure that you do not draw this portion below here, yeah, because they are not like having zero energies. Yeah, just be careful, just be aware of it, yeah. Okay, so it's always the difference between the two. Yes. Okay. Okay, you might not understand what is dihedral angle. Actually, I used the term earlier on, sort of defined for you as well using the Chem 3D. So I think over here, it's quite clear what exactly is dihedral angle. So basically, it's the angle made by the plane, the two CH planes, lah. Okay. Yeah. If you look at a staggered or eclipse conformation, you will know what we are talking about. Okay. Yeah. And then we have discussed some of this. Okay. So of course it's good for you to understand, although not mandatory, the difference between torsional strain and steric strain, or what we call van der Waals repulsion or van der Waals strain. So torsional strain is related to the destabilization due to eclipsing bonds. Okay. Of course, steric strain is the atoms repelling each other. It could be atoms or it could be groups of atoms. Okay, because the electron cloud are sort of forced to overlap with one another because of close proximity, and this will lead to unfavorable repulsion. Right. Okay. So with that, we're gonna move on to something a little bit more exciting. Maybe, I mean, I won't say it's super exciting, but it just increase in difficulties, lah. So that is the conformation of butane. Okay. So again, I'm going to use Chem 3D because it's easier. As I said, it's always easier if the student get to see a diagram. Okay, so I'm going to paste this over to Chem 3D. Okay, so again, we have something like this. Okay, so over here, what I'm going to do is I'm going to highlight the dihedral angle over here. Okay, and then I'm going to do the same thing, the rotation. Okay. Dihedral angle drivers. Okay, yeah, something along those lines. The values here are a proxy. Actually, I should I did not do the minimization of the energy. I should have done it first. Okay, so I'll do it already, and then now I'll do the rotation, so you'll make a little bit more sense. Okay, right. So okay, I'm just going to rotate this here. Okay, just going to shift this up like this. I'm not sure whether it's very clear to you. Yeah. Okay. Okay. Basically, some of you might be wondering actually how to see. What are we actually rotating? Okay. The point of reference, right? It's only meaningful if we know what we are looking at, obviously. Okay. So I'm just going to rotate it like that. Okay. So basically, these are the two carbon we are looking at. Okay. So I'm just going to put it like this. Can you actually see some sort of like a Newman projection being attempted to be drawn? A Newman kind of projection. Okay, so a Newman projection will be like this is in front of us. Okay, so that is carbon, and this is the CH3 group, and then HH, and then behind us there's a carbon, and then the HH projecting at the back, and then below there's a CH3. Okay, you notice that for molecules bigger than ethane, right? The groups bonded to the carbon in question, right? Other than H, it's a methyl group in this case. Okay, so the methyl group is very big, right? I hope we all agree on that. Yeah, so when the two methyl groups are actually pointing away from one another, so that is somewhere here. So this is probably the most stabilized conformation. And then if I'm going to move it, you notice that when I move it, right, it's going to be more and more destabilized until a certain point, okay, over here. Okay, this is something like eclipse conformation. Do you notice the methyl group over here is directly knocking at a H? Okay, and then the two H's are repelling each other, and then of course the H is repelled by the methyl group. Do you notice this is very unstable? Okay, so as we approach downwards again, it becomes more stable, but as we rotate the back clockwise, it becomes more and more unstable. I think we can understand this, right? Okay, I'm going to rotate further, and then we're going to get a new kind of staggered conformation. Do you notice this is actually staggered? If you are able to look at it in terms of perspective, it's something like it's somewhat staggered, but maybe not quite yet. Okay, now this staggered conformation, right? Okay, you notice that it's not very stable. Do you notice? It's like, okay, it's not as unstable as when the H and the methyl group are opposite each other. Yeah, but it's not quite as stable as when the two methyl group are trans to each other. Do you notice that? Yeah, so despite being a staggered conformation, it's actually quite unstable. Yeah, but because it's still staggered, yeah, it's like better than having the torsional strain where the H and the CH and the CH3 are pointing each other. Yeah, so this is still a staggered conformation, but we give it a special name. Later on, you learn that it will be called gauche conformation. Yeah, so it's G-A-U-C-H-E. It's not pronounced as gauche. It's called gauche. Yeah. Okay, and then if I rotate further, obviously it's understandable why this is the most unstable. Okay, because the methyl group are facing each other. Okay, you can see that the van der Waals electron cloud is actually overlapping. So this is the most unstable conformation. And then if I go down further over here, I'm reaching another gauche conformation. Okay, like this. Okay, so this methyl group is very near to this methyl group, although they are 60 degrees apart, but ideally the bulkiest group should be put opposite each other. Okay, so this is another gauche, and then of course this is another eclipse, and then finally we are back to here where the methyl group are opposite each other. Okay, so this is the conformational analysis of butane. Yeah, so if I were to sum it up a little bit, you notice that earlier on we talked about ethane, and then in ethane we discuss staggered and eclipse conformation. Yeah, and the difference between them is about 12 kilojoules per mole, and we explain why, because the repulsion between the CH group is about 4 kilojoules per mole. Yeah, and then we went on to discuss butane, which is a little bit more advanced. Okay, so now we're going to go back to our lecture notes. Okay, you guys can read through. I'm not going to go into details because this graph is quite similar to what we discussed earlier on. Okay, yeah, so this is the term, the gauche conformation. Yeah, so I think learn to use this term, gauche. Okay, there's a term which I didn't introduce to you. Okay, when the two CH3 are trans to each other, opposite each other, like this, okay, or like this, yeah, we give them a special name. We call it anti. Okay, the anti-conformation. Okay, it is still staggered. Notice that the anti-conformation and gauche conformation are all staggered kind of interaction, conformation. Yeah, but there is a difference. Okay, and this repulsion, okay, normally for chemistry, we tend to draw it like this. Okay, yeah, so when we draw this particular sign like this and like this, we are actually trying to say that there exists electronic repulsion between the two groups. Okay, if you are wondering how to draw, it's basically like a C like that. Okay, so if you have problem drawing, just talk to your tutors. I think we can help you with that. Normally we don't show it for everything. We don't like anyhow show like that. No, we don't do that. Okay, we tend to show it for the most significant interaction like this and probably like this. Okay, yeah. Okay, so the rest are details. We won't go into them. Okay, so if you are interested, you can like go through the notes over here. There is also the most unstable eclipse conformation. We call them SYN because the two CH3 group are in the same site. Okay, so we won't go into details as well. Yeah, just ensure that you are familiar with the terms gauche, anti, and SYN. Okay, now conformation of ring systems can be a little bit complicated. Yeah, the focus of H3 is on 6-membered ring. Yeah, so because the focus of H3 is on 6-membered ring, I will not attempt to discuss a lot about cyclopropane and butane, etc. Yeah, but what I can show you is that most of you visualize butane as a cyclobutane, sorry, as a square, right? And then you might think that it is flat, but it's actually not flat. Okay, so let me just show you using Chem 3D. So I'm going to draw a cyclobutane out over here, and then I'm just going to paste it into Chem 3D. Okay, just going to release this Chem 3D, right? If I paste it in over here and I do a minimization of energy, right? Do you actually notice that it takes on like a puckered conformation? You know, like a puckered. It's not exactly flat. Can you see? It's not flat. If I look from the side, it's not flat. Yeah. So no matter how the molecule, no matter how strained the molecule looks, right, it will try its best to remove it from taking on unfavorable eclipse conformation between any of the two groups. Okay, so if I'm going to measure the dihedral angle, okay, let's say for this, right, you notice that I'm clicking this, and oops, sorry, I think I need to put the shift sign. This, and this, right? You notice that the angle is actually 23.2. So it forces itself to take on a certain angle. You notice that it's not zero. Do you notice that it's not zero? Yeah. So where possible, molecules will try their best to be as stable as possible. If let's say you say, okay, this is not this is not the worst case. So let's say we look at cyclopropane, right? Okay, we can do that as well. Okay, yeah. So with that, can you see that there's some angle being made? 10.7 degrees. Can you see that? Yeah. So to the best of its ability, it will try to reduce. Yeah. Okay, so there's some angles. Yeah, so it will try to remove itself from the unfavorable repulsion that it experiences with one another. Okay, so if that is something that you interested in, maybe after you graduate or even now, free time, you can try to take a look at some of this computational chemistry related stuff. Yeah, but again, as I mentioned, cyclopropane, cyclobutane, all these, they are not in the syllabus, so do not emphasize too much on them. Okay, cyclopentane as well. Okay, but cyclopentane is a little bit better because cyclopentane, because the ring is bigger, right? So the different carbon chains is a little bit more flexible to take on a conformation that is the so-called the most ideal given its circumstances. Yeah, so for cyclopentane, not too bad, but again, not the most stable ring system. Cyclohexane is the most stable ones, and we'll get to see them later on. Okay, actually right now. So I'm going to show you cyclohexane over here. So I'm just going to show you cyclohexane. Okay, I'm just going to plug it in, and then yeah, so this is cyclohexane. I'm going to do a minimization, a simple one. Okay, can you see that for cyclohexane, right? Okay, I'm just going to zoom in. Can you see that between every of the carbon, right? Okay, so can you see that the carbon is labeled as carbon 5? There's a number to the carbon, right? Okay, so let's begin with carbon number 1, and then behind is carbon 2. Can you see that over here is staggered? Okay, correct? Yeah, so it's 60 degrees, almost 60 degrees. It's not 100% 60. It's not exactly 60 degrees. If you don't believe, I can show you the angle. It's not 100% 60 degrees. It's about 50-ish. Yeah, that's close to 60 degrees. Not too bad. Okay. Yeah, so it's close to staggered, at least within your visible eyes. Okay, I'm gonna rotate and put carbon 2 in front and carbon 3 at the back. Okay, so behind is carbon 3, huh? So this is carbon 3. Can you see another staggered conformation over here? I'm gonna rotate again Okay, this carbon 3 and this carbon 4, right? Can you see another staggered conformation? I'm going to rotate carbon 4 and 5 at the back now. Can you see another staggered conformation? And then, of course, 5 and 6. Can you see another staggered conformation? Yeah, and then I rotate back. So this carbon 6 and carbon number 1. Can you see another staggered conformation? And then we are back to 1 and 2. Yeah, so between any of the carbon pairs, you're going to get a staggered conformation. Yeah, so that's the main thing of cyclohexane. And that is why it is the most stable. And that is why when you go and study any introductory organic chemistry course in university, they will normally start you off with cyclohexane because it's like the easiest to discuss. Okay, yeah, so but easy is one thing because now I have computer, right? But what is difficult here is about the drawing lah. Yeah, how do you draw the chair conformation? And every batch we tend to have students who have not so nice drawings lah. So I think I just hope that over here, right, we can actually try to guide you through in the drawing of the chair conformation. Of course, we'll do that in the lectures as well, in the actual lecture, in the face-to-face lectures. But over here, hopefully at home, you can do a bit of practice. It does help a lot if you can practice on your own. I mean, no amount of lectures or talking will be able to help you to draw unless you get your hands dirty. Okay, I'm just going to use the blanks space over here to help you do a little bit of translation. Okay, so there are normally two things you need to learn how to draw lah. How do you draw a simple chair conformation for cyclohexane? Okay, and of course at the same time, how do you translate that conformation into a Newman projection, which can be quite difficult for students. Okay, so again, I'm going to shift over to Chem 3D. Okay, because if I shift to Chem 3D, it can be easier. I mean, it can be easier. Okay, so I'm just going to rotate it to try to fit into this. Okay, with this CH2 pointing downwards. Okay, so like this. Can you see? Yeah, so this CH2 is pointing downwards, like this. You might be wondering why is it called a chair, right? Okay, so can you see that this is like the headrest, then this is the place where you sit, and then this is the place where you place your leg. So if I tilt it a little bit more, now you can see it's like a chair where you can rest. Okay, that's why we tend to call it the chair conformation for that reason. I mean, nothing fanciful. Okay, then how do you actually draw the chair conformation? Can I say, how do you draw it easily? Well, I think the first thing you need to do, right? Maybe I can just put it over here. Okay, the first thing you might want to do, right, is to check out the obvious position of the groups pointing up or pointing down. We call them the axial hydrogens. Okay, the axial bonds. So you notice that okay, there are many ways to draw. Okay, the easiest way people tend to draw the chair conformation, right, is, I think number one, right, they try to sketch the carbon framework out first. Okay, so you can just Google or even watch millions of YouTube channels on that. Just bear in mind that whatever people say is what they think is the best and it's the easiest to draw for them. And of course, we also have other, I also created other YouTube videos on how to draw the chair. If you wish to, you can look at them. But over here in the lectures, I'm just going to bring you through what I think is the simplest way. So the simplest way you can draw is just to outline the chair in this fashion. Okay, like this. Okay, this is like a Concorde, if you know how a Concorde looks like when it's begin to fly. Okay, like a Concorde. Okay, so the easiest way is really just to draw this portion out first. Okay, then after that, right, you complete it by drawing the rest. Okay, I'm drawing on a computer screen, so it's not so easy to draw, so I hope you don't mind. Yeah, and then what normally people will tell you, and of course that's the truth also. I mean, I'm not trying to say that people are wrong or what, that there will be three pairs of bonds that are parallel to each other. So this is parallel to this. Okay, this is parallel to this, and this is parallel to this. Of course, the question is, must I use a ruler to draw? No, please do not use ruler to draw because it will look very odd. Yeah, you can draw freehand. We are not going to measure whether is it really parallel. We're not going to do that, of course. Yeah, but I'm just saying that aesthetically, right, it should be near to parallel. Okay, and then after that, take note that each of the carbon, right, takes on a tetrahedral geometry. Okay, so once you do that, then you're just going to use red to draw in the H, what we call the axial hydrogens. Okay, so this is an inverted tetrahedral geometry, so I draw the H down. Okay, so this is the hydrogen. Okay, and then the neighbor will be pointing upwards, and then of course the neighbor will be pointing downwards, and then up and down and then up. Yeah, I think this is the number one thing you need to be clear about. How to draw the axial hydrogens. Okay, yeah, so it alternates lah, so it's up down up down up down. Okay, then after I'm going to change to a green pen. I'm going to draw the equatorial hydrogens. Okay, remember that this is an inverted tetrahedral, so therefore the H should be pointing in this direction. Okay, this is an upright tetrahedral, so H is pointing here, then this one is pointing here, here, and then of course in this case it's over here and then over here. Yeah, okay, so this is a little bit tougher because remember just now when we drew the axial, I was telling you that it's down, up, down, up, down, up, right? Yeah, but it seems that equatorial there's no down, up, down, up, down, up. No, it's not correct. There is also down, up, down, up, but it's at it's close like a 45 degrees kind of angle. Okay, so this is considered up. Okay, then this is down because it's pointing in this direction. Okay, and then this is up, down, up, down. Okay, so there is still up, down, up, down, up, down for equatorial position, but it just takes a bit of time for you to get used to. Yeah, is that alright? I hope that's okay. Yeah, so because of that, I'm just going to show you this. Can you now see that this is down? So this is the red one, and then up, then down, and then up, and then down, and then up. Correspond to the red one over here. And then the equatorial one is actually pointing in this direction, so it's up, and this is down, and then this is up. Okay, you can't really see this as up, but it's like projecting 45 degrees upwards towards you, and then this is projecting 45 degrees downwards away from you. Okay, then this is projecting 45 degrees upwards in this direction. Okay, and then this is downwards. Yeah, so it's exactly like what we have discussed. Okay, so this is very important to draw the chair conformation, and you need to learn how to draw it well. The two most difficult hydrogens to draw, right, if I can emphasize, okay, is actually these two, this hydrogen and this hydrogen. There are a lot of students who draw them in the wrong direction. Okay, like for example, they may draw this in this direction, or they may draw this in this direction. How to actually prevent yourself from drawing in the wrong direction is actually quite straightforward. So I learned this when I was in university. Okay, so you can view this, you can view a certain alphabet out from the conformation that you have drawn. So for example, this H, right, this is like M. Can you see? Like this. Yeah, so this is an M. Okay, so therefore, if I point like that, it's no longer an M, right? Yeah. And then for the other way around, it's like a W. Yeah, so if you are able to do that, then you will not draw incorrectly. Okay, how do I translate this to the Newman projection? Same thing. Oh, sorry, it's supposed to do Chem 3D, right? Okay, so I'm just going to rotate it like that. Can you see? Can you see? I'm going to rotate it like that. Can you see? I have two Newman projection already. Yeah, okay, over here. Can you see that they actually correspond to each other? Yeah, this carbon is here, H is pointing down, behind the H is pointing up, and then this H is pointing down, behind the H is pointing up, and these are the two green ones here. And then this CH2, you don't have to draw them out, you can just put them as CH2s, no issue, no problem with that. Okay, yeah, so this is how you translate to the Newman projection. But of course I'm toggling between the Chem 3D and then the actual drawing. You might be thinking that it's not as easy as it seems lah. I mean, I perfectly agree with you that, you know, half the time it may not be as easy as it seems. Okay, but let me assure you that you will improve over practice. Okay, so maybe I can just do a translation from here so that you know that it's not just talk, but it can actually be done quite easily. Okay, so let's say I put my eyes here. Okay, so I put my eyes here. Okay, I put my eyes here. Okay, then what's going to happen is that over here, right, the H is pointing down. So this is carbon 1. So let's say this is carbon 1, right? H is pointing down. And then this H is pointing up. Okay, so this H is pointing up. Okay, and then at the back, I'm going to use maybe blue. At the back, the H is here. And then the H is pointing up. Okay, okay, I hope that's fair enough. Okay, and then after that, right, I'm going to use a different pen. Like this, right, is to the CH2. And then I'm going to draw it down. And it's straight away connects to carbon number 3. So this is 2 and this is 3. So this H is pointing down, which is here, and then the other H is pointing up. And then I'm going to show you the behind one. So this is 1, 2, 3, and then 4, 5, 6, right? So carbon number 6 is at the back, right? But here is pointing downwards. So it's pointing downwards to carbon number 5. And then it's connecting to carbon number 4 at the back over here. Can you see? So the H is here, this H is here, this is the H, and then the other H is here, which is this H. Okay, so you can actually translate it on your own and in any ways you want. You'll notice that the one in the lecture notes can be a little bit confusing. Again, as I said, it is the way they chose to look at it. But I feel that putting the eyes here is actually more difficult. It's actually easier if you put your eyes here to draw the Newman projection out. Yeah, so if you wish to, you can do that on your own. And then, like just compare what you have. The thing about conformational analysis is that sometimes your answers can be different from your friends, but both can be correct. Yeah, so that is the so-called the beauty of it. But so that also means that that doesn't mean that you can anyhow draw. Yeah, because you need to find your own voice in drawing, which is very important. Okay, yeah, I don't want to go on and on because I tend to go on and on when it comes to this. And of course, the drawing of the cyclohexane is illustrated here. So again, if you need any guidance, please talk to your tutors. I think I've gone through with you the step-by-step in drawing. Yeah, so page 10, I think I will leave it to you all to read. And then there is also another conformation that is important for cyclohexane. It's what we call the boat conformation. As we know, there's infinite number of conformation, but one will be more stable than the other, of course. Yeah. So what exactly is the boat conformation? So okay, so we can actually flip this upwards. Okay, and then you get the CH2 like near each other, right? And then this whole thing looks like a boat. Yeah, so it's called a boat conformation. So it's not very stable. So what it's going to do is C4 will be flipped downwards. Yeah, so this is known as a ring flipped. Students tend to extremely dislike doing the ring flip because they tend to get it wrong. Yeah, so I think what is important here is practice how to do the ring flip. Okay, literally not exactly using the model. Okay, because you cannot use model in exams, but to do that on paper on your own, it's really a lot easier. Okay, so we'll look at a lecture exercise. Okay, so for this lecture exercise, what we're going to do is, okay, so draw two different chair conformations of cyclohexanol. So label the OH as axial or equatorial for each conformer. Okay, so what we're going to do now is I'm just going to draw cyclohexanol out. Okay, so OH like this. Okay, like this. Okay, so this is cyclohexanol in the skeletal structure. Okay. Now, the first thing you need to ask yourself, right? And that is, of course, the basis of this exercise. The first thing you need to ask yourself is does this molecule have a chiral center? Okay, so of course the answer is no. It doesn't have a chiral center. Yeah. Why? Because this portion is symmetrical. Okay. Whether you go from the left, clockwise or anti-clockwise. Clockwise or anti-clockwise. You end up counting the same group throughout. Okay, so there's no chiral center. So if there's no chiral center, right, when you draw your conformation, the most stable conformation you will draw is definitely having the OH group at the equatorial position. why is that the case lah? Yeah, and that is something we did not discuss earlier on. Okay, so we're going to so-called discuss it now lah. Okay, so let's say I call this carbon number 1, 2, 3, 4, 5, 6. It's actually your call where you want to put carbon number 1. It's your call, or rather where you put the OH. Because there's no chiral center, right? You can actually put it in any of the position to your likings lah. Yeah, but of course the easiest way to do it is of course to put it here, because it's easier to count. So this is 1, 2, 3, 4, 5, 6. Yeah, just make sure that wherever you put, right, your numbering is in order. So meaning that let's say you put here, and then when you look at your own skeletal structure, it's clockwise counting. Make sure you also do it clockwise lah. Yeah, don't do it the opposite. Although in our case here, it doesn't matter, as I mentioned, that it's not chiral center. Okay, and then how do you do a ring flip? Okay, you do a ring flip by, again, you flip this part downwards, and then you flip this part upwards. I mean, it seems easy lah. I mean, like easy for me to talk about it, but when you draw it out, it's not that straightforward, of course lah. Now the beauty when you do a ring flip is that any groups in the axial position, right, will end up in the equatorial position. Yeah. So after you perform a ring flip, right, so what's going to happen is that now my OH group will be here. Now remember that it is pointing up here, right? So it should also be pointing up here. You do not change the configuration. But again, in this case, let me repeat. In this case, it doesn't matter because there is no chiral center. Yeah, do you notice that? There is no chiral center, so it doesn't matter. So you'll notice that, and this is also where students have the most common misconception. I draw the H out. Students will think that, so is a ring flip just switching the OH and the H? It looks like it, right? Okay, why do I say it looks like it? Because if I flip the structure 180 degrees, like let's say I flip up like that, then I'm going to end up with something like this. I'll draw in pink. Going to end up something like this. The OH is pointing down. Okay. Correct? OH is pointing down, right? Carbon number 4 is still here, right? But carbon number 5 become here, you know. And this is 6th. And then this is 2 and this is 3. Okay. You notice that the counting of the atoms are different. Here is clockwise, here is clockwise, here is clockwise. They now become anti-clockwise, right? Yeah. However, because there's no chiral center, so it doesn't matter again. Yeah. So that is why there is a danger when students do this particular lecture exercise, right? They might, okay, I use the word they might lah. I'm not saying that they will. They might have the misconception that ring flip simply means changing between equatorial and axial. So they just draw instead of this, they just draw this. It's not the case. Okay, I'm going to explain or just showcase to you using one little example. Okay, why, you know, sometimes when you have this misconception, right, you will end up drawing the wrong isomer. You end up drawing the enantiomer instead of the actual structure. Okay, Ken, I'm just going to illustrate it here. I know it's not being asked in the lecture exercise, but I think it's great to break this misconception. So what I'm going to do now is I'm going to erase the non-essential parts, okay, like all the arrows. I'm just going to keep the main stuff so that you will be able to see what we are doing now. Okay. I'm going to give my OH a configuration. Okay, I'm going to let it be pointing upwards. Okay, and then I'm going to introduce another group deliberately lah. Okay, so again I purposely do it lah. Okay, I'm going to introduce this group at carbon number 3. So maybe I erase this 3. Okay, I just put a 3 here. Okay, I'm going to introduce this group also pointing in this direction. Okay, just put Cl. Okay, can? Yeah. So remember that OH is pointing up, right? So my OH is pointing up. So my structure is still correct. Now it's just that carbon number 3, I have a Cl. Okay. Yeah. I need to check my configuration. Okay, because the one and the OH and the Cl are pointing in the same direction. Okay, do take note of that. And their relationship is clockwise. This is important because if you anyhow draw, you end up the enantiomer. Okay, so they are clockwise. If I do a ring flip, like what we have done here, right? You'll notice that the OH is pointing up, right? Still pointing upwards, although it's now equatorial. Now, where is the Cl? The Cl will be pointing in this direction. Okay, I hope this is clear enough. Okay, and if I flip over, right, flip the thing over, then my OH, instead of pointing up, will be pointing down, and my Cl will be pointing down. Can you see it? And then you might be wondering, how come this is different from this? Like, why is it that one is equatorial, the other one is axial? Well, I mean, of course they are different, because if you look at the carbon, right, this is in clockwise, this is in anti-clockwise. So of course they are different. Okay, then you might be thinking, okay, all these make sense. I can easily draw them. It's not true, you know. It might look deceivingly easy, right? But let's say, right, you have the idea that ring flip simply means swapping the groups, right? Then do you know what you end up drawing? You end up drawing this. I can be quite confident. You end up drawing this. You end up drawing the OH pointing like this, and then the Cl pointing like this. I am quite confident you end up drawing this. So this carbon 1, 2, 3, 4, 5, 6. You end up drawing this. But did you actually realize that when you drew this, right? Okay, what you are drawing is actually the enantiomer. What do I mean? So this is actually the enantiomer of this. If you, I don't know, I give you maybe a minute or two to think about why is that the case. Why is it the enantiomer? Okay, then after you sort of can see, then maybe we can discuss further, hopefully. Yeah, I'm not sure if it's obvious to a lot of you, but it is actually the enantiomer. Yeah. What can we do to help you see that it's actually the enantiomer is what I'm going to do is I will try to draw this in this manner. Okay, so meaning I'm going to just turn it around so that the counting of the carbon is also remain as anti-clockwise. Okay, I thought that will be that will be easier because if that's the case, then you can actually tell. Yeah, so if I actually draw it here, right, over here, which unfortunately I don't have the space, you'll notice that the OH is here. Okay, the OH is here, right? OH is here. Okay, and just going to try to draw it out in the best possible manner lah. I mean, as in I can't do it in the best way. Okay, I'll try to draw the mirror image for you to see. So this is 1, this is 2, and this is 3, right? So the 3 is a Cl. Okay, and then this is 4 and 5 and 6, right? Yeah. Do you actually realize that this mirror image, in terms of the molecular structure and the projection in space, is actually the same as this? Do you notice that? You try to fit it in, it's actually the same. Yeah. So when a chiral center is present, right? If you try to draw the ring flip product by flipping the equatorial and the axial position, which is very bad habit, okay, and you should not do that. If you simply just flip the positions of the axial and equatorial, exchange the position, then you end up drawing the enantiomer of the products or of the conformer that you want to draw. Okay, I repeat, if there are chiral centers involved, and you try to draw your flip product by simply exchanging the equatorial and the axial groups, right? Then you end up drawing the enantiomer of the flip conformer that you want to draw. Yeah, so that is something I just hope that you'll be able to see, hopefully. Yeah. Okay, yeah, so I will move on. Okay, one thing I didn't explain earlier on, right, is why is it that the ring flip product is more stable. So that means, okay, so if I can just erase lah. Okay, so why is it that, maybe I would highlight, why is it that this is more unstable as compared to this lah? Okay, the reason is, I think number one, right, when the axial groups are pointing vertically up, they experience unfavorable repulsion. Number one is with one another, and then of course number two is with the hydrogen involved lah. Okay, with the hydrogen that is pointing outwards. This is known as 1,3 diaxial interaction. Okay, it's a very big word, but yeah, learn how to use it. Yeah. Okay, so this is the 1,3 diaxial interaction we're talking about. So even if you try to put the bulkiest group in the equatorial position, there still exists 1,3 diaxial interaction, but this is like better than nothing lah. Yeah, but if you flip the bulky group over here, then there will be unfavorable 1,3 diaxial interaction between the bulky group and the hydrogen bonded to carbon 3 and 5. Okay, so I think this you can read through on your own. Right. This will be quite difficult, so we won't go into discussion. Maybe we'll do that in the tutorial. For trans and cisdecalin, I don't think we'll discuss it over here. Okay. Now, for exercise 2, right? Okay, number one is draw both chair conformation and then indicate which is more stable. Okay, so I'm just going to do the same thing lah, as in it's really easier. So I'm going to number the carbon. So this is carbon number 1, okay, carbon number 2, 3, 4, 5, 6. Again, the numbering of the carbon is arbitrary. So it's up to you. If you don't like this as 1, just call it 2. You know what I mean? Like if you want to do anti-clockwise, just do anti-clockwise. Like nobody's going to care how you number it. Okay, then I'm going to draw a nice chair conformation. Okay, a nice chair to the best of your ability, of course. Okay, so again, my drawing cannot be nice on when I draw on the screen. It's difficult to control the pen. Okay, so I hope you will bear with me. Okay, now so we number the carbon. Okay, so 1, 2, 3, 4, 5, 6. Okay, and then we put in the groups. Okay, now CH3 is pointing downwards, so this is CH3. Okay, right. This is pointing downwards, away into the plane of the paper. Oh, okay. Br at carbon 3 is pointing upwards, so this is Br. CH3 at carbon 5 is pointing upwards, so CH3. Okay, yeah. Then of course, in this particular conformation, the two bulky group are in the axial position, so they will experience unfavorable 1,3 diaxial interaction. So we're going to do a ring flip. Okay, probably I'll draw this longer. Okay, when we do a ring flip, remember, equatorial become axial, axial become equatorial. So I'm going to draw this out like this. Okay, okay, and this is still carbon 1, 2, 3, 4, 5, 6. Okay, and then the CH3 over at carbon number 1 will be pointing downwards. Carbon number 3, the Br will be pointing upwards. Carbon number 5 will be pointing upwards as well. Okay, so you'll notice that when you perform a ring flip, the group's position where they point does not change. They do not change. Okay, so CH3 over here before the ring flip is pointing down. CH3 over here after the ring flip is still pointing downwards. Okay, of course, when you are trying to draw the structure, the conformation that is, you might not number the way I number. Okay, do you notice that you might notice that I'm a bit biased here. Okay, I start off with this as number 1. Okay, so you might be wondering, right, what if you start this with number 1, this is 2, this is 3, this is 4, this is 5, and this is 6. You might be wondering if this is possible. This is definitely possible. Definitely possible. You can do that. Nobody is stopping you. Okay, but if you do that, there's something you need to change, because CH3, remember, is pointing downwards, right? So your CH3 at carbon number 1 cannot suddenly be pointing upwards like this. Okay, because it's supposed to point downwards. So this will still be pointing downwards. Then carbon number 3, the Br will be pointing outwards. and then carbon number 5, the CH3 will be pointing upwards as well. So this CH3. Okay, so this will be the answer if you choose to number it. If you choose to shift the carbon numbering position by 1 clockwise. Can I shift further? Can I let this be carbon number 1? You can do that. Then all the groups will shift. Just remember that you must be consistent in what you're doing. That is the key. Okay, your answer can be very different from your friends. That is not important. Yeah, as long as you know what you're doing, you'll be fine. Alright, so which is the most stable? Of course, I think it's quite obvious. This is the most stable. Of course, I'm talking about this as well. Yeah, because I am minimizing the number of axial groups. Okay, because axial groups have unfavorable 1,3 diaxial interaction. Okay, yeah. Then in the next lecture, we're going to talk about cis-trans isomerism. It will not be too different from what you learned in H2. Yeah, but just do watch the lecture because we are going to go through the CIP rules.